Hello everybody. Before we begin quantum mechanics, let me ask you something simple. Do you think physics was complete by the end of the 19th century? If you are thinking yes, you're wrong. Because at that time, Newtonian mechanics explained motion, Maxwell explained electromagnetism, and thermodynamics explained heat. Many physicists believed that physics was almost finished, only small details were left, but it was not. Let me tell you what happened. When physicists thought that entire physics has been done, physics has been given, everything has been done, almost the entire physics has been done. At that time, nature started refusing these laws. That means the laws which were given before. So, in this lecture, what are you about to study is not just a subject. It is physics admitting its own limitations. Welcome to quantum mechanics. You're finding it strange? Yeah, it's obvious. I do find it strange as well. So let's begin our first lecture of the quantum mechanics, in which we will talk the introductory things about quantum mechanics. Well, classical physics works beautifully for our everyday things like everyday objects, machines, planets, projectiles, and all. But when we go to the atomic scale and subatomic scale, that means we are talking about very small things. It fails completely. Let me give you some examples. We have got some examples where classical mechanics fails and we needed a special sort of physics. That means we needed some sort of things which would explain the things at a very small levels. That means atomic and subatomic level, and from where the need of quantum mechanics came in. So let's talk about those examples where classical mechanics actually failed, and the need of a new sort of laws, a new sort of trends which were observed by the physicists came in and explained the things at atomic and subatomic levels. And the best example is blackbody radiation. First of all, let's talk about what is blackbody radiation. Imagine if we are hitting an object, okay. As it gets hotter, it starts glowing. You can't see it glowing because I'm not hitting it at that temperature. First red, then yellow, and finally white. This light emitted by a hot object is known as blackbody radiation. Now talk about what is blackbody. It was really hot. Okay, so blackbody is an ideal object that absorbs all radiation falling on it and emits radiation depending only on its temperature. Why I'm talking about these things and what it has to do with the quantum mechanics? Okay, so the thing is, the classical mechanics failed to explain this phenomena. That that's why quantum mechanics has to make the entry and come in and explain the things. So let's talk about what classical mechanics predicted about the blackbody radiation and what quantum mechanics explained, and whatever the quantum mechanics explained was experiment based. That means the data stored by the experiment was explained by quantum mechanics and not by the classical mechanics. So let's talk about what the experiment says and what the classical mechanics had predicted. Okay, so let's talk about what does experiment says. So based on the experiment, the scientists found three things. First thing first is, at low frequencies, the radiation was very small. That means the intensity of the radiation was very small, and at medium frequencies they got a peak. That means the radiation was maximum. And when they go to very higher frequencies, that means at very higher frequencies the radiation went to zero. That means the intensity became zero. So if we would draw a graph based on the intensity and the frequency, we will get a hill graph. It would be like it's your low frequency thing where intensity is minimum, and sorry, I won't say minimum, intensity is small, and when you will go to the medium frequency, the intensity will be maximum and we will get a peak, and then at a very high frequency the intensity will go to zero. Now talk about what classical mechanics predicted. Okay, so Classical physics used two theories. First of all, the first one was Maxwell's electromagnetic theory, and the second one was classical thermodynamics. And it said energy is continuous and every wave gets equal energy. That means law of equipartition of energy was used here. That means with every degree of freedom, half kT of energy is associated with it. And this idea led to the Rayleigh-Jeans law as well, which is very famous. According to this law, intensity increases with increase in frequency. That means as the frequency increases, the intensity also increases, and it's continuous, which will give us a result that at higher frequency there will be more energy and the intensity will be maximum of the radiation. So we can arrive at the conclusion from the two things we have discussed, that was what experiments said and what the classical physics predicted. And it was the classical theory predicted that very high energy at high frequencies, infinite energy in the ultraviolet region. That means in ultraviolet region the frequency is very high, okay, and the wavelength is very low, so the energy would be infinite because of the high frequencies, what predicted the classical theory. But the experiment said that radiation drops at higher frequencies and energy is finite. And this huge mismatch is famous with the name ultraviolet catastrophe. So let's say it in a satirical way. Classical physics said more and more energy with frequency and the more energy forever, but nature said no, energy stops increasing, man. Now we have talked about the problem. So what was the solution? How the quantum mechanics came as a solution? So here comes a very great legend, Max Planck. You must have heard about Planck's constant. Yeah, that's the man we are talking about, Max Planck. He said that energy is not continuous, energy comes in packets, and the packets is called quanta. The word quanta means packets, and he gave us a formula for energy which was E equals to NH mu, where mu is the frequency, H is the Planck's constant, 6.62 into 10 to the power 10 to the power minus 34 joule second, and N is the quantum number. So energy is given in packets, not continuous. And with this theory, with the quantum solution of given by the Max Planck, the experiment was matched. So classical physics failed to explain blackbody radiation because it treated energy as continuous, which led to infinite energy at high frequencies. This problem was solved only when energy was assumed to be quantized, and this work was done by Max Planck. Okay, so if you like this video, then like this video and subscribe to the channel, and we will upload more videos of quantum mechanics. This was just a trailer and I got really crazy. Quantum mechanics has got so many blasts and we are just talking about theoretical things right now. Okay, so there is no certainty here of the next video coming as I have promised. There is only probability. Okay, as a subject is probabilistic, the things are also probabilistic that the video will come or not. But I will try to upload the lecture with certainty, and there is probability of this certainty as well. Sorry, I'm confusing you, but you have to be used with this confusing things, because there is going to be a lot of confusions, a lot of strange things, and you are going to be a part of it. So thanks for watching this video, and you can expect to have more videos in this series, and those will be better and better and better further. Next video will be, I guess, on board, and marker will be used and no FaceTime thing. Okay, fine. Have a good day.